Okay, so we're in the age of big data, which large amounts of data being collected by satellite imagery, remote sensing, automatic data loggers, citizen scientists. And we've got the situation where there is vast amounts of data being collected, but there's a problem in how we potentially extract knowledge out of this data. So this expression, drowning in data, but starved for knowledge. There is also another, these are sort of these throwaway advertising type of slogans almost. David Buckingham, I'm not quite sure who he is. I did look it up a year or so ago, but I've forgotten, probably because I didn't think it's worth remembering who he was. His expression, data is the new oil, or we need to find it, extract it, refine it, distribute and monetize it. So a very business orientated view onto data, and to say that we can create money out of it, we can do things with this data and make money out of it. So a very economic argument. I much prefer David McCandless. David McCandless is one of the sort of data viz gurus of the modern age in this TED talk, who refutes the other guy and says data is the new oil. No, data is the new soil, in that the data itself is not particularly the value, although there may be value in data. It's what you can make from that data that is the most important stuff. How do we extract the information out of that data to make useful things? The data in itself is not really the most important thing, although obviously it's vital for the extraction. So how do you extract knowledge from vast amounts of data? Well, there is a history of trying to do this in computer science. And the main methodology has been the idea of data mining. So here, the aim of data mining is to make sense of large amounts of data in some domain. This has come from business environments, so it's mostly been developed for extracting information from business systems to inform business knowledge. And the whole of the data warehousing talk kind of is in the domain of business, although it is being used in other domains as well. So basically, you take graphical and data mining is the idea that you take graphical and numeric techniques, make them relatively easy to use by domain professionals, who then use these techniques to explore the large data set that the company has supplied. So data mining is known by many different other names, also known AKA, also known as, in case you don't know what AKA means, knowledge discovery, all these different descriptions. So this is a subject area where data mining may return the papers that you want if you're doing a keyword search, but also these other terms, in particular business intelligence is one of the widely used terms for this kind of undertaking, because it comes from the business environment. That's where it developed. Just a quick slide just to make sure what I'm talking about, the difference between data mining or data exploration and inferential approaches to analysis. So in your research methods, you'll probably be emphasizing inferential analysis, in which you develop some kind of hypothesis, you go out, you collect some data, primary, secondary data, doesn't matter. Then you come up with some sort of test to formally test the hypothesis that you had given your data. And this involves often using the smallest data that gives sufficient confident estimates to either accept or reject your hypothesis. That's your classic scientific method. But in this environment, we're talking about more exploratory approaches. So this is the situation where you have a whole load of data. The data set is large, it's often messy. And the question is, how do you find patterns in that data which then may allow you to develop hypotheses that you can test through a formal testing system? So it's about finding patterns in data and then which then allows you to then take an alternative approach to see whether those patterns are real and what processes potentially create those patterns. And basically what you do is you build small, simple models that describe the data, the large amount of data. So it's just a contrast. Okay, business needs and databases. So far this year, mostly this module, we've mostly been talking about what are called OLTP databases, online transaction processing databases. These are the everyday databases that companies use for recording sales and whatever other business things they do on a daily basis. It's updated on a constant fashion. It's a live database, and it's usually in normalized form because we want to maintain integrity of the data, and that's important that we manage that data integrity when we're capturing data. So this is your OLTP, online transaction processes. Data transactions and data integrity are the emphasis. But you're a manager and you want to understand patterns in your sales or whatever your business is undertaking. That is not a useful environment within which to do that because of the constant changing of data and also the way the data is structured into highly normalized data structures. And as we know, normalization introduces, it gets rid of data duplication and redundancy, but it introduces complexity in the data model. So what happens is we have an alternative shadow database called a data warehouse, which basically we extract the data out of the business transaction system that we need, we clean it up, we tidy it up, we make it nicely accessible, we organize it to emphasize data query and exploration, and then when we discover some sort of something, some pattern or something through our data mining or analytical techniques onto this structured database, onto this query, this database that we've designed specifically to enhance our sort of data, our exploration, that may feed back into how the business strategy and how we run our business in general. So two types of basic databases: online transaction, online analytical. Okay. So the data warehouse, what is it? So this is a definition, Inmom's definition. 4 things, he says: subject orientated as opposed to transaction orientated. Your database is designed to address a particular question, business question or set of questions. So it's not about maintaining all the transactions, it's about asking questions of your whole business. Integrates heterogeneous data from multiple sources. So it's brings stuff together into a single place where the managers can query and investigate it. Time variant. Okay, this is coming from a business environment, but it's true for many situations. Primary business needs to predict which data items will be located into. So basically, time is an integral part to these warehouse databases because they, particularly from a business perspective, because you're trying to work out how, say, retail patterns have changed in the past so you can predict what you want to do in the future. Non-volatile. Data are read-only and only periodically updated from source. So we only update our warehouse once a month, once a day, once a year by extracting the data we need out of our transaction-based system. Here's a diagram of a basic warehouse architecture, which we'll run through quickly. This is from Vasilius' Business Intelligence book. So we start off, data. We have internal data extracted from our transaction databases, other types of corporate databases, personnel records, vehicle records, if you've got a vehicle fleet, whatever. Many organizations hold many different types of databases. Maybe personal databases collected by the manager who's sitting on his desk, on his desktop in some kind of Excel spreadsheet or something like that. Then there may be external information, market share from some kind of market share company, all these consultancies, maybe the census information, maybe ordnance survey base mapping. So we have these various diverse sources of data, also different data formats, potentially, data structures. We have to load these into our data warehouse, and there's a set of tools called ETL tools, extract, transform, load, that assist you in extracting useful subsets of data from databases, transforming them, so that, for example, changing control vocabularies so that they match each other, getting rid of duplicated records, finding missing data, finding values that don't fit into domains, and things like that, and then loading it into the data warehouse. If you went over to see Surrey County Council a couple of weeks ago, I had a chat with one of the guys there who was using one of these ETL transform load systems, and it was really interesting. He was running this load thing, and you were seeing which records were being bumped out at which stage along the workflow. So if you saw that, that was the sort of thing that I'm talking about. There's some really sophisticated tools for doing this thing. And it cannot be, I cannot underestimate how much effort is involved here in setting up these advanced ETL loading schemes. A lot of effort is required finding all the sort of idiosyncrasies that might exist in the various data sets that you're trying to load and integrate. So you have to load into your data warehouse. Your data warehouse is a clean, consistent, static data set that's historical in that it shows you trends through time. So your transaction database, maybe you're only storing, in your transaction bases, you're not interested in transactions that happened 10 years ago. Say if you're Amazon, you're only interested in active people's purchases, things they've got on their watch list, things that they've got in their basket, things that's in transit, things that they might want to return up to a month later. Any data that's older than maybe 2 months, you don't want in your transaction database because it's just seizing things up, making it bigger, making it more unwieldy. But if you're talking about overall patterns of business, how your business patterns are changing through long periods of time, you need to store all the historic data in your data warehouse. So it's historical. There may be some aggregation. We'll talk about aggregation in due course. It can result in a very large database, gigabytes to terabytes. And one of the things about that we're going to concentrate on is that these data warehouses are often created in a non-normalized schema. We use something called a star schema, in which facts are identified in various dimensions. And we'll cover that in due course. So it's a different database schema that's optimized for usability, understandability, and query and consistency. Oh yeah, metadata. Yeah, well, okay, all this loading, getting data from internal databases, getting external data sets, shoving them through ETL transaction loading tools. We also need metadata that describe the data sets that we have in our warehouse, where they've come from, what is the process being used to load them up, the ETL process, what transformations have been done, who owns them, standard things, but also we've got the documentation on the warehouse itself, how it's structured, and potentially the usage of the warehouse itself. So you have a metadata system, just like on any other databases, we have a metadata system, we have a metadata system on our warehouse. Finally, once we've got, oh, I've missed one out. Okay, did I miss one out, or did I just? It's just I just went too far. Okay, so we have this warehouse. Star, and with the star schema in it, we'll talk about star schema in due course. We then have views onto the warehouse for the different user groups. So we may have, and these are called marts, data marts in the terminology, because it's come from business and shopping and things like that. So we may have the logistics unit involved in shipping and trucks and stuff like that, may have one view onto that data warehouse because they're only interested in a subset of the data in it. Marketing may have another view. Quality assurance may have a third view. These views may be for different groups by task, as we have here, but also by geography. So it may be by region or something like that if you have a regional structure to your company. So the marts provide the sort of user-specific views onto the data warehouse, and then we have the mining tools that we use to interrogate the data that we see through the views. So the sorts of things that mining tools are interested in is things like identifying outliers, particularly odd values in our data sets, descriptive statistics, graphs, finding clusters, summarizing and aggregating the data to different spatial and temporal scales, for example, classifying sales by something, trends, changes in trends through time, predicting the future, and something which is used a lot, which I know nothing of, association analysis, which is basically what else is in your basket if you bought big bubble bath. You know, consumers tend to buy similar sets of items. So there's a whole variety of tools, and I'm not talking about these tools in this lecture. I'm talking primarily about the data warehouse, not the analytical tools. Stars and cubes. So we're looking, this is where you hold your head up, it's not to hold your head. So the concept of a data warehouse is that your data exists, the data that you're interested in, the facts that you're interested in, exist in a multi-dimensional space called a data cube. It's called a cube, but it can be 3-dimensional, 4-dimensional, n-dimensional cube. Multi-dimensional cube. So here's a 3-dimensional cube, in this case from a paper which is up online on user-centered spatial data for environmental research. So we're interested in water quality, some measures of water quality, say dissolved oxygen, the amount of dissolved oxygen in the water. Those are our facts, how much dissolved oxygen is in the water, for example, and that fact may be identified in these dimensions, located in these dimensions. So where I took that sample and got that value, it happened that sample was taken at a particular time, the dimension of time, in a particular watershed, a dimension of watersheds, and that the place was, say, in some type of land use. It was on a farm, so it was a farming land use, so there's a dimension of land use. And in this database, they have 4 dimensions. They have one called time, one called watershed, one called land use, which I've shown on my cube. There's also one called stream, which is which stream. It's a hierarchical representation of a stream network, which I can't draw a 4-dimensional cube. It is possible to draw a 4-dimensional cube on a piece of paper, but it's very hard and it's difficult to actually understand what you're looking at. So I've only shown 3 of those dimensions. So we can take that, one of our data points, and it exists, if we're just talking about 3 dimensions, it exists in this cube somewhere. Yeah. Think of a scatter plot, basically. Oh, this is annoying when this happens. Okay, sorry about the state of the slides. So the fact table, this is about the fact table. Okay, so the fact table stores the thing that we're interested in this case, water quality values. Okay, all measurements in that fact table must be at the same, what they call grain, which is scale. So, for example, if I measured a water sample, it would have to be measured in the same way, or at least an equivalent way. Okay. I couldn't take, for example, so each sample, so if I went down to the hogs mill, I could take one sample and get dissolved oxygen at one location. I could also take several samples up the river, combine them together into one sample, shake it about, then get the average water quality. Those are not equivalent grains because one is for a 1-point location, the other one is spread across several locations and is an average. So it's a more general measurement. So all measurements must be at the same grain, and we'll talk about grain a bit more in due course. Most measurements are numeric and additive. What do I mean by additive? They have numbers that can be summed together in any way you like, because data mining is mostly about investigating aggregated values rather than individual values. It's about getting to sort of, so therefore these figures tend to be additive and are best if they're additive. See some more of that. Okay, here's an example of I told you it's all business orientated. Here's a sales fact table, sample factor. So we're interested in how many of some item was sold in a store each week or whatever, or each day. So we've got the quantity of the item sold and the amount that we got for selling those products. We've also got here each thing each day. So this is, we're counting up how many things are sold each day. So we have a date key here for what day of the week it is, what day it is. We have a product key, which is what the product is that we're recording. Is it Fairy Liquid? Is it Pure Soap or something like that? And we have a store, the store at which the sale was made at. So we have a day, the product, the store, the quantity sold, and the amount of money, dollars in this case, that was sold for. And that's our basic example of a fact table. Oh, sorry about